As the first speaker, I am here from Rippling. I am going to talk about React Compiler. I'll just start sharing my screen as well. Cool. So I'll begin with my introduction. So I'm Sweta. I am working here in Rippling from past around 3.5 years, and I'm a senior software engineer. I work on React Native tech stack. So today I'm going to talk about basically how you can compile smarter with React Compiler. Cool. So I hope you all are aware of React Compiler. If not, so this talk is going to cover how this React Compiler is a game-changing innovation in the React development. So the agenda is going to be, we are going to talk about the challenges which we face in React performance, what React Compiler is, its key benefits, the impact which it has. We'll show a small demo how it works, some few tips and best practices, few limitations, some troubleshooting, and at the last, conclusion. So to begin with, we all acknowledge that the biggest problem in React development is performance. So React's declarative nature, while simplifying the UI creation, it leads to what we call the re-render cascade or the domino effect. This happens when a small state change in a parent component triggers a chain reaction. That is, your parent component somehow it changes, and every child component inside it, it's going to change or it's going to re-render. That is a domino effect. One thing changes and everything in that particular hierarchy changes. So historically, and in fact, today also we are relying on the manual memoization techniques, which are use memo, use callback, or react.memo to combat these things. Now, these tools help prevent us the re-rendering when the props or dependencies haven't changed. However, applying them correctly is like a major challenge, and it introduces significant developer overhead because now I have to take care of, like, I have 5 functions. I have to make sure either they are wrapped in react.memo or use memo or use callback. Now that is a developer overhead for me because I have to make sure whether this component or this function needs memoization or not. Now, this is where the React compiler steps in. Its core promise is same code, faster by default. And now this is not just a performance tool, but it's a philosophical shift. Now, what exactly is React compiler? Or you can call it automatic optimization. So it's a sophisticated build-time tool that automatically optimizes our React applications through memoization. Now, this is a crucial distinction. The optimizations are baked into your application bundle before it even runs. So it's not a runtime tool, it's a compile time tool. At its heart, what it does is it performs a source-to-source transformation. That is, it takes your original JavaScript or your TypeScript code, understand the common React idioms like hooks, JSX, and then intelligently rewrites it. Now, it is designed to automatically inject the memoization logic, similar to what we would manually do by adding the use memo, use callback, etc. Now, a key aspect of its sophistication is its deep data flow analysis. This allows it to understand which inputs truly affect which outputs, focusing on semantic value changes rather than just strict object identity. Now, this is huge because it addresses a major pitfall of manual memoization whenever a new object references, even with the same content. Another important thing is the compiler operates under the fundamental assumption that your code adheres to the rules of React. Basically, it assumes that you all are aware of React rules, the rules of React, and you are following them, basically, which are immutability and the pure functions. Now, this is important, but here's the brilliant part. It has a built-in safety mechanism as well. If it detects violation or deems a component too complex or unsafe to optimize, it won't do anything. It will gracefully skip the specific component or hook and will assume that you are going to handle it so that your code remains untouched and nothing happens over there. Now, the key benefits. If I talked about its key benefits, they are the enhanced developer experience and the user experience. So from a developer experience perspective, the primary benefit is a significant reduction in cognitive load. Now, we no longer constantly need to remember that I have to add these memorization techniques. Now, this frees up mental capacity of ours, allowing us to focus on core application logic and features development, which means we can write cleaner, more concise code and without any boilerplate. Another less obvious but powerful benefit is its proactive bug detection. The compiler strictness in optimizing components that adhere to React's rules can surface existing bugs, such as data races or hidden issues caused by excessive re-rendering that were previously masked. Now, from a user experience perspective, the benefits are direct and tangible. The automatic optimization means a smoother, more responsive user interface characterized by faster page loads. Now, these are some quantifiable impacts and some real world performance gains. So this is the meta internals data where your INP, which is interaction to next paint, when used with the React compiler, they saw 15% reduction, coming down from 275 milliseconds to 240 milliseconds. Now, this is a crucial metric for responsiveness because this is an impressive reduction. Next, we had the largest contentful paint, which is LCP, which measures perceived load speed, which was improved by about 10% from 2.6 seconds to 2.4 seconds. Now, from the Sanity Studio case study, an internal metric called EFPS, which is editor frames per second, which measures responsiveness during editing interactions, showed a remarkable 20 to 30% increase. Now, these numbers are not just statistics, they represent the tangible improvements in user satisfaction and your application success. Now, we have talked about like its benefits, what exactly it is. Now, let's see what the live code demonstrations, how visually what it does. I'll start with a basic example. So I have a very slow component in the top where what it does is just like a while loop where it's just printing something, a very slow component. Now, if I talk about how you're going to render it, the very basic case, you have a parent component with you. You have a counter where like if I tap on the button, you're just incrementing the counter value and you're just rendering it. Now, let's add memoization over it. What would be the memoization techniques we are going to apply? We are going to use memo, use callback, or React.memo. Now, let's apply over it. Sorry. So if you just see over here, my very slow component is exactly the same as it was before. What we have done is we have wrapped this component into React.memo, basically manually memoizing this component. Then we're just calling this button so order to make it work. Now just to see and just show you what exactly is going to happen if we don't have any memoization techniques in place. So whenever you're going to tap on this button, it is going to log this particular value. So let's just take this example over here with us. So this is my screen without memoization. I have this increment counter button. I'll just show the logs as well. Now without memoization or anything, if I tap on increment count, I can see every time we are tapping on this button, this log gets printed. But it should not happen, right? Because we're not changing anything on it. Now coming back, let's add memoization on it, which is here. Now, after memoization, I'll just clear this. I'm tapping on it and nothing is happening, right? Oh, sorry. Cool. Yeah, just zooming it. So here, this is my UI screen. So here, this is without memo. This is with memoization. I'm tapping on this increment count button, and there are no logs because we have added use memo. We have basically memoized that particular function component. Now, where exactly does now React compiler comes into place? Because we're able to do what we wanted to do with these memoization techniques. Now, let's do what React compiler would do. We're going to use the same code, the previous code, without any memoization technique. And if I'm going to run it, it's going to work exactly the same as it was working before. In order to show you how it exactly works, there is a React compiler playground, which helps you understand what happens when you are using no memoization or anything. For it, I'll just remove these memorizations which we have added. Now, there's no memoization in this particular screen component. So I'm going to show you the mapping of these components. If you see the screen, The left side, so this is basically how the React compiler internal working is. Now this is my very slow component, and in the left side, in the right side, if you see, this is how it works. You are importing C as underscore C. So underscore C is basically my the way I'm going to make it work with the components. Just give me a moment. Correct. I'll just go to my code in order to show you the proper comparison. So here, in the top, there is my component, the original component, and here I'm having, in the bottom, the compiler's code, how it is mapping over it. You guys can see the screen, right? Now, if you just see, the compiler introduces this underscore C parameter, which is basically to manage a cache. Now, on the first render, it computes and stores the JSX element, which is T0, which is over here. And on subsequent re-renders, if the component inputs have not changed, it retrieves the cached JSX, skipping the expensive loop and JSX creation. And this is react.memo. Now coming to the parent component. So we have applied memoization in your very slow component. Now the parent component where it uses. Now in the original parent component, changing the parent state would have caused the entire function to re-execute, basically recreating all its JSX components and forcing the very slow component to re-render. But this is a React compiler's equivalent. If you see on the top, here we have used underscore C7. If over here it's going to be more visible. It is not. Yes. So here the compiler allocates a large cache in the parent component to manage the multiple memoization paths. Now, all of the tags, your H2 tags, your P tags, every tags are going to be memoized. And the button and the very slow components, these are also memoized. So basically, the compiler extracts the inline functions, like our set count callback, into stable helper functions. Now, this ensures their reference does not change with every render. If you can see, there's a temp function as well. By help of this, it ensures that the reference does not change on every render, which is crucial for effective memoization of the button's on-click prop. So ideally, we have not written any memoization technique on the left side, but the React compiler, it detected the code that here we can add memoization. It internally added all the memos which it could have added. If I search over here, see, it added react.memo. A lot of places it added memoization so as to make sure that all of the code can be memoized and we as a developer don't have to undergo through all that overhead which we would have gone. Not only that, even this top level wrapper, the compiler, this my app, even on this, if you just see at the bottom, it has applied the memoization. It caches the parent component also, ensuring that it only recreated if necessary, so that further optimization of the entire application can be done. Now, in a sense, the React compiler performs deep analysis to automatically inject memoization at a granular level wherever it can find possible, and it handles the complexity of the referential equality, which allows us to write cleaner code. Now, in order to fully leverage the React compiler, what can we do? Few of the best practices which we have felt. So first and foremost, adhere to the rules of React, which means prioritizing immutability, prior functions, and having strict null checks. Next, we have to make sure a critical nuance, which is when to keep the existing memoization and when to use the React compiler. Now, it is generally recommended to retain any existing use memo or use callback when you are working with the dependencies which are with the use layout effect. Effects rely on referential equality, and the compiler's internal memoization might subtly differ, potentially altering the effect behavior. So for functions that perform truly expensive computations and are used across multiple distinct components or hooks, considering implementing their own external memoization, but always you have to make sure that you profile first as well. Next, whenever you're writing new code, trust the compiler that it is going to memoize for you, although you have to make sure that your code is cleaner and following to the rules of React. Leverage the ESLint plugin, which is the ESLint plugin React compiler. It has very good warnings and errors, which directly indicate any code problems or any code patterns which might prevent optimizations or signal the violations of React rules. And finally, continuous E2E testing. The compiler can sometimes surface previously hidden bugs or alter the memorization behavior in subtle ways. So if you have a robust E2E, that can help you make sure that your code is robust. Now, although the React compiler offers significant advantages, it is important to understand it is still in RC, it is still in beta phase, not a beta phase, but still in development phase. And there are still current limitations and potential pitfalls. The most prominent one, which is reported, are usually compatibility with external libraries. Not every library has adopted React compiler and the optimizations. For example, the tan stack table, it breaks due to in-place mutations. Now, compiler, it does not transpile the third-party libraries. You might be using tons of libraries. It's not going to compile that. It is just going to use your code. Then we have unexpected behavior, which comes with the effects. If the compiler's automatic memorization produces different referential identities, which is when we're using use mem or use callback, that can lead to some UI issues. Now, the compiler is designed to gracefully exit or gracefully skip over components or hooks which are having issues or which could break the rules of React. So you're not, that component of yours is not going to be optimized and it's not going to fail your component as well. So it gracefully skips it so that your logic or your code remains untouched. Now, crucially, the compiler does not solve prop drilling. While it optimizes the re-renders, but it does not inherently change the architectural problem of passing over the props through multiple layers of the components. And finally, debugging the compiler-related issues can be challenging if your end-to-end tests fail without clear error messages. Now, these are some troubleshooting the common pitfalls which we just talked about, where I've specified the root cause, few impact which it might have, and some solutions. So if we start with the compatibility with external libraries, root cause is like they don't have the in-place state mutations, which leads to your broken UI functionality. And the solution will be disable compiler for specific libraries. Then if you see unexpected use effect or use layout effect behavior, it's likely because your compiler's automatic memorization differs from what your effects expect. The recommendation here is to retain your manual use memo and use callback. Then when the compiler skips optimization, it is usually because your code violates the rule of React or is too complex. Fix is to review your ESLint warnings and refactor solutions like the context API or state management libraries. Now for difficult debugging, especially when E2E tests fail without clear messages, again, leverage the ESLint plugin React compiler and employ the binary search in order to filter out that particular root, the problem which you might have. And finally, to avoid unpredictable behavior on compiler upgrades, especially if your test coverage is low, make sure you pin down the version of the React compiler. Now, in conclusion, the React compiler represents a significant leap forward in the React development. It fundamentally transforms how performance optimization is approached, shifting the burden of micro optimizations from the developer to the build tool. Its core benefits are pretty clear, that the reduced boilerplate, the cleaner code, enhanced DX, and your faster UX. However, it is important to remember that the compiler is not a panacea. It requires adherence to the rules of React. Again, to repeat, its immutability and the pure functions. You all should be aware of that and apply it. And for us as React Native developers, embracing the React compiler means building high quality mobile experiences with minimal complexity. It allows us to achieve instant performance benefits in existing applications. And to maximize its benefits, remember these key takeaways, which is embrace immutability and pure functions, utilize ESLint plugins for proactive feedback, strategically manage the dependencies, retaining the manual memorization whenever necessary, trust the compiler for new code, and finally, prioritize robust E2E. Thank you.